Hey everyone, so we're at video 6. In the last video, we spent a lot of time. Honestly, it was a deep dive, talking about the basement of storage. We talked about how bits actually hit the physical metal, the physics of the SSD, and how B-trees and LSM trees manage the chaos of persistence. But today I want to move up one layer. I want to talk about how we as humans organize that data. I want to talk about the taxonomy of storage.
See, if you're a junior or mid-level engineer, you're often told that the first step in building an app is choosing a database, right? And usually that choice is made based on what's popular, or what your friend uses, or what the last company you worked at used. You pick Postgres because everyone says it's solid, or you pick MongoDB because you heard it's flexible. But choosing a database because of its vibe or its brand name is, well, it's not engineering, it's fashion. As a first principles engineer, you have to realize that every database is just a set of trade-offs wrapped in a specific data model. And the model you choose is the single most important decision you will make because it dictates how you will think about your data for the next 5 years. I want to start with a very fundamental question. What is data? At its core, data is just a collection of facts about the world. User 1 has the name Andre. Andre bought a coffee for $5. These are just facts. But the way we store these facts depends entirely on one thing. How do we plan to ask for them later? In system design, we call this the access pattern. This is the first principle of video 6. Don't choose your database based on how the data looks, choose it based on how you intend to query it. If you get this wrong, if you put graph-shaped data into a relational bucket or document-shaped data into a key-value bucket, you are going to spend the rest of your career writing complex, slow code just to fight the database. You're basically going to be swimming against the current. So let's start at the beginning of the modern era of storage. We have to talk about the relational model. This is SQL. Now, I want you to imagine it's 1970. Before this, data was just a mess of pointer spaghetti. If you wanted to find a piece of data, you had to follow physical memory addresses. It was a nightmare. Then, a researcher at IBM named Edgar Codd wrote a paper that changed everything. He said, what if we treat data as a set of mathematical relations? This was a radical idea. He suggested that we should store data in simple tables, rows and columns. And here's the key. Every row in a table should be unique, identified by a primary key, and we should use foreign keys to link them together. This led to the concept of normalization. If you've been in the industry for a few years, you've probably heard of third normal form, or BCNF. It sounds like academic ivory tower stuff, but the first principle of normalization is actually quite beautiful. Store every fact exactly once. Think about why that matters. If I store Andre's address in 5 different places, and Andre moves to a new house, I have to find all 5 places and update them. If I miss one, the database is now lying to me. It has inconsistent data. Normalization solves this by saying, put the address in one table and give it an ID. Everyone else just points to that ID. This is the relational dream. It gives you data integrity. It gives you ACID transactions, atomicity, consistency, isolation, and durability. It means that when you save data, you can sleep at night knowing the database won't lose it or corrupt it. But, and there's always a but in system design, the relational dream has a tax, and that tax is the join. I want you to think about what happens inside the machine when you run a SQL query with 3 joins. The database has to look at table A, find a pointer to table B, go to a different part of the disk. Remember video 5? Random I/O is slow. Find the row in table B, then go to table C. SQL is amazing because it's flexible. You can ask any question you want. Show me all users who bought coffee on a Tuesday and live in Seattle. You didn't have to plan for that question when you built the table. The relational model can figure it out. But that flexibility comes at the cost of random I/O. As your data grows to millions or billions of rows, those joins become incredibly expensive. This is the impedance mismatch. Our code in JavaScript or Python thinks in terms of objects. A user object has an array of orders, and each order has an array of items. It's a tree. But SQL thinks in flat tables. To turn those flat tables back into a tree for your code, the database has to do a lot of heavy lifting. So, for about 30 years, SQL was the only game in town. But then, around 2005, something happened. Google and Amazon started hitting the limits of the physical universe.
Amazon realized that their shopping cart didn't actually need the full power of a relational database. They didn't need complex joins. They just needed to be able to save a cart and read it back instantly, every single time, even if a whole data center went offline. This led to the NoSQL rebellion, and the first child of this rebellion was the key value store. Think of a key value store like Redis or AWS DynamoDB as a giant distributed hash map. It's the simplest possible taxonomy. You have a key, like user123, and a value, which is just a blob of bytes. From a first principles perspective, the key value store is the fastest thing in the world. Why? Because there are no joins, there's no searching. You give the database the key, it runs a hash function to find exactly which server and which spot on the disk holds that data, and it gives it to you in O of 1 time. It's a direct hit. But here we go again. The tax for this speed is limited querying. If you want to ask, show me all users who bought coffee, a key value store can't help you unless you've specifically built a key for that. You can't search the values, you can only get the key. This is the trade-off. SQL says, give me your data and I'll let you ask any question, but it might be slow. NoSQL says, tell me exactly what question you're going to ask and I'll give you the answer instantly, but you can't ask anything else.
This led to the second child of NoSQL, the document store. Think MongoDB or CouchDB. Document stores were born from the frustration of the impedance mismatch I mentioned earlier. Developers were tired of splitting their user object into 5 different SQL tables. They said, why can't I just save the whole JSON object as one chunk? This is the concept of data locality. In a document store, everything related to a user, their profile, their settings, their last 5 orders, is stored together in one physical spot on the disk. When you ask for user123, the database makes one trip to the disk and pulls back the whole tree. No joins, no random I/O. For a junior dev, this feels like magic. I don't have to design a schema. I can just dump my JSON. But this is a dangerous trap. See, document stores trade normalization for locality. If you store the user's address inside the user document and also inside the invoice document, you now have redundant data. If the user moves, you have to update it in 2 places. If you forget one, your database is now inconsistent. And here's the bigger problem: relationship management. Imagine you're building a social network. You have users and posts. You store the last 5 comments inside the post document for speed. But what if a user changes their profile picture? Now you have to go through every single post document where that user commented and update their picture URL. This is what I call managing the join in application code. You saved time on the database query, but you've added massive complexity to your code to keep the data in sync. So when do you use a document store? You use it when your data is self-contained. If a piece of data doesn't really have many relationships with other pieces of data, like a blog post or a product description, document stores are amazing. But if your data is highly interconnected, a document store will eventually become a nightmare of data corruption and manual syncing. Speaking of interconnected data, let's talk about the most niche but fascinating taxonomy, graph databases. Think Neo4j. In a relational database, relationships are a secondary thought. They are just IDs in a column. In a graph database, relationships, edges, are first-class citizens. They are physically stored as pointers. If you want to ask, find me a friend of a friend who likes the same music as me and has worked at the same company, a SQL database will scream in pain. It would have to do 5 or 6 joins, and as the table grows, that query will take seconds or even minutes. A graph database doesn't search the table. It walks the graph. It starts at your node and follows the physical pointers to your friends, then to their music, then to their jobs. The speed of the query depends on how many friends you have, not on how many billions of users are in the database. This is the power of the graph taxonomy. It's for when the relationship between the facts is more important than the facts themselves. Now, I want to take a step back and talk about a very common mistake I see mid-level engineers make. They think they have to pick one of these for their whole company. They say, we are a MongoDB shop, or we are a Postgres shop. This is the golden hammer fallacy. If all you have is a hammer, everything looks like a nail. But modern system design is about polyglot persistence. Think about a company like Netflix. Their user profile, name, email, might be in Postgres for ACID integrity. Their viewing history, which is a massive fire hose of data, might be in Cassandra, an LSM tree-based NoSQL store for high write speed. Their personalized recommendations might be pre-calculated and stored in Redis, key value, for sub-millisecond lookups. Their content relationship graph might live in a graph database. They use the right taxonomy for the right access pattern. But wait, I want to get a bit more technical here. There is a new category that has emerged in the last 10 years that tries to bridge the gap. We call them NewSQL. Think CockroachDB or Google Spanner. The engineers behind NewSQL made a first principles observation. They realized that people loved the SQL interface and the ACID guarantees, but they hate the way SQL scales. See, traditionally, to scale Postgres, you had to buy a bigger server. This is vertical scaling. NoSQL scaled by sharding, splitting the data across 1,000 small servers. This is horizontal scaling. NewSQL databases use a distributed consensus, like the Raft algorithm we'll talk about in video 9, to give you a SQL interface that lives on 1,000 servers. It's trying to give you the relational dream with the scaling nightmare. But even NewSQL isn't a silver bullet. You still pay a tax in latency. Because the servers have to talk to each other to agree on a transaction, a write in CockroachDB will always be slower than a write in a single-node Postgres instance. You are trading individual speed for global scale.
So, how do you navigate this taxonomy? How do you actually make the choice? I want you to stop looking at the logos and start looking at your access pattern. I want you to sit down with a piece of paper and write out the 5 most common questions your app will ask the data. Give me this specific thing by its ID. Key value. Give me this thing and all its small details that never change. Document store. Give me a summary of all sales in the last month grouped by category. Relational. SQL. How is this person connected to this other person? Graph. I have millions of users, and I need to update their balances with 100% accuracy. SQL or NewSQL. Most of the time, you'll find that a relational database like Postgres is actually the best starting point. Why? Because Postgres is good enough at almost everything. It has JSON support, so it can act like a document store. It has indexed lookups, so it can act like a key value store, and it has joins, which NoSQL can't do. As a junior to mid-dev, your default should be SQL until you can prove with math and benchmarks that the join tax is killing your performance. Don't leave the safety of ACID transactions just because you think NoSQL sounds cool. Now, I want to talk about something a bit more subtle. Schema on write versus schema on read.
SQL is schema on write. You have to define the columns before you can save the data. If you try to save a middle name and the column doesn't exist, the database says, no, fix your code. This is a first principle of data integrity. It forces you to be disciplined. NoSQL is often schema on read. You can save anything you want. You can save a user that is just a string and another user that is a 5 megabyte JSON object. The database doesn't care. But here's the secret. The schema always exists. It's either in the database, SQL, or it's in your application code, NoSQL. If you use a document store with no schema and you decide to rename the zip code field to postal code, the database won't help you. Your code now has to handle both, if user.zipcode or user.postalcode. If you do this for 5 years, your code becomes a museum of old decisions. It becomes filled with if statements trying to handle 20 different versions of a user document. This is the hidden cost of NoSQL flexibility. It's not actually flexible, it's just moving the burden of discipline from the database to your tired human brain. I want to finish with a look at the future of this taxonomy. We are starting to see a convergence. We see multi-model databases like Azure Cosmos DB or ArongoDB that let you store data as a document, a graph, or a key value, all in the same engine. We are also seeing the rise of vector databases like Pinecone or Milvus because of the AI revolution. Vector databases don't store facts in the traditional sense, they store embeddings, mathematical representations of meaning. If you want to ask, find me images that look like this image, or find me text that means the same thing as this sentence, a SQL or NoSQL database is useless. You need a database that can calculate the distance between vectors in 1,000-dimensional space. This is a brand new taxonomy, and it follows the same first principle. The access pattern, finding meaningful similarity, dictated the creation of a new storage model. So here is your takeaway for video 6. Data is just bits, but the taxonomy you wrap those bits in, relational, document, key value, graph, vector, is a set of physical constraints. SQL gives you rigid truth, integrity, but pays the join tax. Document stores give you locality, speed, but pay the relationship tax. Key value gives you raw throughput, but pays the query tax. Graphs give you connection speed, but pay the search tax. Don't be a fanboy of a specific database. Be a student of the access pattern. Ask yourself, how will I need to look at these bits in 2 years? If you understand the taxonomy, you don't just build apps, you architect systems that can survive their own growth. In the next video, we're going to look at the art of sharding. We've talked about how we store data on one machine, but what happens when you have so much data that it physically cannot fit on the biggest disk you can buy? How do you split the truth across 100 machines without losing your mind? I'll see you in video 7.